session is truly a testament to the city of Kozhikode, because we are the land of spices. We love food. We are all food lovers over here. And we are going to talk about biomanufacturing of food, a delicious revolution. So today we embark on a journey into the future of food production, where science meets gastronomy. Our expert will unravel the exciting advancements in biomanufacturing that are reshaping the culinary landscape. So, ladies and gentlemen, dear delegates, join me in savoring the flavor of this delicious revolution as we delve into the innovations and possibilities that lie ahead. So, a warm welcome to our distinguished speaker. I'll just introduce our speaker. He is Mr. Vishal Menon. He's the Chief Development Officer of Synthite Industries, where he is engaged in the research and development efforts that are linked to building new businesses and brands for the group. So over the past 25 years, Vishal has developed functional expertise in intrapreneurship, strategy, innovation and organizational development across industry domains, as diverse as financial analytics, luxury hotels, information technology, consulting and agri-business. So Vishal is an alumnus of the Indian School of Business, Hyderabad. So ladies and gentlemen, dear delegates, shall we give a big round of applause and welcome our distinguished speaker, Mr. Vishal Menon.
Ladies and gentlemen, how are we feeling? Good? Great. So it's a pleasure to be here in this beautiful city of Kozhikode, and I'm truly honored that I have an opportunity to give you a little talk about the future of food as I see it. I happen to be carrying something in my pocket that I want to show all of you before we start. So I'm carrying in my pocket the future of my company, a future manufacturing hub, a future factory of my that my company is basically going to invest in. So that's what this presentation is going to be. It's about microbial cell factories, right? How do we leverage the power of DNA, power of Mother Nature to create food for the next 50 odd years when our planet is going to have to balance a population of, I don't know, some people say 15 billion people. Right, so that's what this presentation is going to be. So let's just dive right into it. By the way, I'm wearing two hats today. Obviously, the one I was introduced as was the Chief Development Officer of Synthite, but I'm also the Secretary of the CVJ Center for Synthetic Biology and Biomanufacturing, which is an initiative that Synthite has with QSAT to set up a organization that is dedicated as a center of excellence in the area of synthetic biology and biomanufacturing. So that's a little aside. All right. So talking about the biomanufacturing, as is evident with all of you, this is going to be a multi-trillion-dollar industry in the future. One of the McKinsey estimates shows that it's a $2 to $3 trillion enterprise within the by 2030, 2040. Now, given that this is the size and scale of development, it's important for us to just take a step back into what we're really talking about, right? So, biomanufacturing is the engine by which innovative bioproducts are actually brought into commercial scale. So basically what I hold in my hand are these little microbes that when put into a little fermenter generate products which when we go through a process called downstream processing where we extract the products of interest from it. And what is amazing about it is because these microbes are self-replicating, they solve one of the biggest issues in manufacturing. Do you know what that is? It's called scalability. So it's the most scalable solution you can possibly build because the manufacturing unit itself is self-replicating, therefore scalable, right? Secondly, it's sustainable because most of these products actually start from what we call precursors that are usually very, very cheap, right? They could be co-products, from, let's say, sugarcane industry, alcohol industry. So the way we think about this is the cheapest source of carbon and nitrogen that we can get. Theoretically, we can make protein out of carbon dioxide in the air. What an elegant solution to global warming. Don't you agree? So that's the beauty of this industry, and that's why I say with microbial cell factories, we've got scalability, we've got sustainability, we've got biodegradability, and in other words, the most beautiful solution we can hope to achieve, right? So let's just step back and say, take a little dive into the evolution of biomanufacturing, right? Most people know biomanufacturing through its umbrella term, which is biotechnology, but there is a distinction. Now, so biomanufacturing, if you see, was pioneered by some of these people that we have on these pictures. Louis Pasteur, of course, who doesn't know him for the smallpox vaccine, discovered the microbe. Then, of course, you have a guy called Chaim Weizmann. Now, Chaim Weizmann was better known actually for the fact that he was the first head of state of Israel. But he also happens to be one of the most prominent biotechnologists of his generation who created acetone through microbes, right? And then there is Alexander Fleming and do you all know what he made? Anyone? What did Alexander Fleming discover? Penicillin. Yeah, so he was basically the forerunner of antibiotics, right? So that's his contribution. Then, of course, there's a gentleman called Paul Berg who created what we call biomanufacturing 3.0, and he is responsible for recombinant DNA technology. And thanks to him, we have the insulin solution, right, for diabetes, right? So that was part of the technology. And what's most interesting is what these two ladies did. I'm not so sure if they're very popular yet, but in 2020, they won the Nobel Prize for Chemistry. Emmanuel Charpentier and Jennifer Doudna. Now, what they did was something very, very interesting. Now, to abstract a very complex subject, they created something called clusters of regularly interspersed short palindromic repeats. Now, that's a big mouthful for something that is you can create an acronym called CRISPR, and CRISPR-Cas9 is really that technology. Now, just to detect it for you, it's basically a word processor for the DNA, right? It enables you to edit genetic code. Now, going back to class 10, you all know that DNA is comprised of nucleotides, right? Adenine, guanine, cytosine, thymine. These are base nucleotides which in combination basically form the genome, right? The gene and the genome. So what CRISPR does is it allows you to read, write and edit. So there are certain spaces on the genome where you can actually go out and remove a certain piece of that code and replace it with something entirely different. And as a result of that, genes basically use it to code proteins, code amino acids, then go on to code proteins, and proteins are the basis of all life, right? They're self-forming cells at some level. So that's the power of CRISPR. So now that we know a little bit about the word processing, we know a little bit about DNA, we know a little bit about how code can be manipulated to create products of interest. Let's take a look at what this slide says. So this is basically looking at how biomanufacturing can be used in the food system. So in the food system, it's currently used to basically make colors, flavors, preservatives, antioxidants, emulsifiers, texturants, vitamins, sweeteners of all kinds. Have you heard of stevia? So stevia is a sweetener that is now made through biomanufacturing, right, and in huge scale. So over a period of time, you won't have to grow the plant, stevia, and go through that whole process. You can just get it out of a fermenter. And for people who are interested in beer, the beer of the future can come from just one single Saccharomyces cell, which will provide the hops, which will provide all the flavor that goes into beer. So that's how biomanufacturing is going to revolutionize the food production systems of the world, right? So, what's the net end game? The end game is that it'll help make food cheaper. It gives people healthier alternatives, higher nutrition value. So, you see, when we talk about the future of food, we must be cognizant of the fact that you're going to have at least 3 billion people that are going to move from carbohydrate dependency to protein dependency. And what that really is today, if you look at the poorest people in the world, they are largely dependent on carbohydrates for their calorific value, right, for their calorific intake. Over a period of time, as they come out of poverty, they will start demanding protein, right? Because even the poor man at the end of the day, if he can afford it, would like to have biryani, right? He's not going to stick to just having parakanji, the param kanji or whatever that is, right? He's going to demand biryani at some point, right? So there is going to be that impetus on getting low-cost protein. And the only way that is scalable at this point in time is through this idea of biomanufacturing. So synthetic biology in the food industry can definitely help us create safe, nutritious and more delicious food for the future. Yeah, it's a huge sustainability win if we get it right. So here's, I don't want to bore you with the technical minutiae, but effectively it is a very, very complex science. It's a multidisciplinary science that is using the principles of engineering. So synthetic biology, which is an enabler of biomanufacturing, which enables us to build the microbes that go to make those bioproducts that I was describing, is essentially a systematic set of tools, techniques and analytical models to engineer biology, right? So, and that's where you will find that biology today is at the intersect of computer science, machine learning, electrical engineering, because we're borrowing a lot of this idea of genetic circuits and plugs and things like that from electrical engineering. So, this is the toolkit that we've got to work with, and effectively some of these toolkits, I mentioned CRISPR in my explain what that is. Besides that, you've got this idea of modular engineering, where typically you can order from a biofoundry, which is a company that will probably make platforms and allow developers, like you have your app developers in an Apple ecosystem or an Android ecosystem, how they work with on a certain technology platform to develop apps. The same way you'll have biology engineers or synthetic biologists who will work on these platforms that are provided by companies to create these modules, say a chassis. A chassis is basically a bug without anything in it, right? And you can introduce DNA or a nucleus, what we call a xenograft into it, and create an organism that you want, right, towards a certain purpose. So that's the beauty of trying to combine engineering and biology. And it's definitely not without its challenges, right? Because think about it. Just the human genome has 3 billion base pairs, right? And each cell has 2 meters of DNA that is folded and folded and folded into a space of 6 microns, which is 1/10 the size of human hair. So can you imagine something 2 meters long being folded? And then look at the complexities around how you would find, unravel it, figure out the specific codes required to engineer proteins. It's a complex system, but that's where machine learning and computer science is going to help us. So I wanted to give you a more relatable example. So here's something that we do today at our company, for example. So you've heard of vanilla, right? Who doesn't like vanilla ice cream, right? So vanilla is the world's most favorite flavor. It's also, natural vanillin is also one of the hardest things to make or derive from nature. So, and that is because even though it's a highly abundant material from the standpoint that you traditionally get vanilla or vanillin, which is the principal flavoring compound within vanilla, from vanilla beans, You also get it from multiple other plants. They're basically secondary metabolites from multiple plants, right? But they're not necessarily in the form of vanilla. They are in the form of certain molecules that can be treated as precursors that you could use to produce vanilla. So that's what this slide is trying to describe. You've got a moiety called ferulic acid, which exists in something called rice bran. Rice bran is an agricultural byproduct. So it comes when you process paddy, right? So now that rice bran basically contains ferulic acid, which can be converted using microbes to produce this compound called 3-methoxy-4-hydroxybenzaldehyde, which is really your vanillin. Now, and that we do by using intermediate bugs, microbes. So what we do is that we engineer the microbe to produce enzymes. And we use, different ideas. There is the idea of metabolic engineering, there's the idea of genetic engineering and synthetic biology. So we use various tools to enable that bacteria to convert ferulic acid using specific enzymes into vanillin. And that's what this slide is describing. So the question is now, why do we bother doing that? So let's see what is the eminent benefit. So this is typically how a farmer today or a traditional food system today would create natural vanillin from vanilla beans, right? You would take a cutting of vanilla, you would grow it for 2 to 3 years. It would produce these green beans that you see, the second picture. Then those green beans, which are susceptible to a lot of diseases. I'm sure some of you who have visited Wayanad and places like that are aware of, some of these vanillarias there and how much of struggle they've had with fusarium and various other diseases. Once the green beans are formed, you then have to allow it to stay on the vine for almost 6 months. And then after harvesting it, there's another 6 months of curing that happens to convert that into a vanilla bean that is brown in color. That is the cured vanilla bean. And then that vanilla bean is basically taken to a factory and extracted to create vanilla extract. And your vanilla extract is then further isolated and purified to create vanillin. So look at the problems that this supply chain has, right? You've got climatic conditions. And remember that most of the vanilla, I would say almost 70% of the world's vanilla comes from one tiny island called Madagascar. It's off the coast of Kenya, right? So effectively that's 70% of the world's supply. Now you've got problems there with political instability, you've got problems there with climate, hurricanes, things like that, sends the vanilla prices shooting. So your poor ice cream manufacturer who wants to use natural vanilla is sitting here and wondering, is this product going to cost $100 tomorrow? Is it going to cost $500 tomorrow? Who knows, right? Because it's so unpredictable, the market. It also has high water and land requirements. Then you have problems with pesticides and herbicides that are used on the plant, which carry over into the extract. You've got inconsistent quality issues. You also understand that it's prone to disease, as I mentioned, and each vanilla pod has to be hand pollinated. So imagine that every single vanilla bean is a product of somebody actually pollinating the flower with their hands, right? And that's how you ultimately get this product. So clearly has its problems, is not the most sustainable product in the world. Now what's our solution from a biomanufacturing perspective? So what we do is we derive our natural vanillin from an agricultural waste called rice bran. It takes us where it would take, several years to actually develop from a full life cycle, product life cycle perspective. Here we have this product ready in 1 to 2 weeks. So what we've done is that we've isolated certain bacteria that have a proclivity to produce this or convert this what we call cinnamic acid moieties into smaller molecules, and we then literally select through throughput screening the best of the breed, if you will, the ones that have the best characteristics of conversion. So that goes through a very, very intensive strain selection process, which is all happening in these tiny little fermenters. right? So we've got this little, what we call high throughput fermenting vessels. We keep putting this liquid through the system, and for days on end, we would run hundreds and hundreds of such ferments and figure out which is the most efficient at producing vanillin. Once we've identified that, and this process we call metabolic engineering. Once we get that, then that strain is then used to further scale it up. And unfortunately, biology doesn't work like chemistry. Biology has a mind of its own. So there is no concept of dynamic scaling in biology. So sometimes, what works in 100 grams doesn't necessarily work at 100 liters, doesn't definitely not work at 10,000 liter scale. So you go through a huge process of actually scaling this from start to finish and finding your most optimal strain. So, but then look at the benefits. The benefits are that it's unaffected by climatic conditions. It has minimal land or water requirements. You have absolutely no risk of contamination, consistent quality, and that's the beauty of using microbial cell factories. They are very, very precise. There is no, if you've engineered the product to create a certain output, you can be guaranteed it will produce that output. Maybe the quantities will vary, what we call titers will vary, yields may vary, but the quality of the product from a chemical nature will be consistent across years, right? So that's a huge benefit. And then of course we have a green extraction process, which we call DSP, downstream processing. So this yields a product that is 25 times cheaper than the product from your vanilla bean. So this is just an example of what we can do with biomanufacturing. And just so you know, we are not the only ones in this space. This is a list of startups in the US and Europe that are currently, as of today, working to change your food. So what you get on your plates in the future are going to be affected by what these guys are doing, right? They are thinking about making their meat, like making chicken, but not from chicken. They're going to culture chicken in a little fermenter. It's going to taste like chicken, look like chicken. You will be none the wiser for it. Interestingly, it costed $330,000 to make the first biosynthetically derived hamburger back in 2013. You know how much it costs today? $9. So that's the power of and the speed of innovation in this space. And it's still not cheap enough, right? Because $9 means $50 to a retailer, right? To a McDonald's. And that day hasn't come when consumers will pay $50 for a Big Mac, right? So effectively, we are a little bit away from getting there, but we are getting there all the same. So this power of this technology is incredible. I mean, just to give you another aside, back in 1990, it took 13 years and close to $450 million to sequence the human genome. Today, you can do it in 24 hours and for less than $200. You can do it. All you have to do is take a little buccal smear and then send it to a sequencing lab, and they'll give you your genome mapped up for $200. That's the power of innovation in this space. And this is my last slide. Effectively, what it's showing is the challenges or the counter to what I'm saying really about democratizing this space. We have a lot of issues with consumer acceptance. You have issues with ethics. You have issues with the whole idea of regulation and various things like that, which is still a little barrier that we'll have to cross. But hey, isn't that the same for any industry, right? Even the calculator was seen as a threat in the 60s to some people's jobs, right? People are saying that today IT workers will be out of a job thanks to AI, right? It's not going to happen. But those ideas and those threats are still what they are, and I just put it out there. So thank you so much for your patience, and I appreciate it. Thank you very much. Do we have time for questions or?
Yes, I think we can have a question, yes.
Okay. Fire away.
Sir, I would like to know how synthetic biology and CRISPR-Cas9 technology is going to revolutionize a tantalizing food recipe for all of us. Tickle our taste buds, or how the futuristic barley, the genetically modified barley contributes to different flavors of beer or wine. So what are the scope of synthetic biology and CRISPR-Cas9 gene editing tech in that area of flavor enhancers?
Okay, so beer and CRISPR, interesting question. Thank you for that. So what can CRISPR do for your beer? So I'm going to talk a little bit about what is actually happening today, right? So today, what you do in the beer industry is that you use a type of beer, and if you guys know the brand Carlsberg, so they have their own yeast called Saccharomyces carlsbergensis, which is the father of all lager beers, right? Bottom fermenting beers. So so that's the traditional type of bug that goes into the manufacture of beer. But today with synthetic biology, you can actually take this plant called the hops, which contains two compounds called limonene and linalool. These are the principal flavoring compounds in hops that gives beer its characteristic bitterness. So by taking the specific gene from the Humulus lupus plant, which is the hops plant, you can insert that into Saccharomyces carlsbergensis and create a bug that can create a hoppy beer. So with one beer, with one bug, you can make a beer that you can just drink straight off without adding any additional flavors. Right? So that's possible to do today. You can also work towards engineering this bug for very high levels of malt, very high levels of sugar, because you need to have a certain amount of fermentable sugar, which in this case is maltose, in order to get the characteristic flavor of beer, right? So these are things you can do. Yeah.
Sir, what about making wine sort of divine by making synthetic biological innovations?
Making wine.
A wine a sort of divine. Making wine divine with a divine flavor.
I'm sorry, I'm not sure I understand.
Sir, making a wine of divine flavor.
Wine of divine.
Divine flavor.
Divine flavor. Sure. I mean, you could make, I think most wine is of divine flavor anyway if you drink it, but then you could. I mean, if I get your drift right, I'm guessing that you could technically make wine, without alcohol using bugs. You can make wine with any flavor that you want. Now, if I want to make a vanilla flavored wine, I need to figure out the specific genes that make vanillin, the flavor component, and insert that into a grape wine.
I am hinting on the church wine.
Church wine.
Okay.
Yeah, but church wine is, pretty flavorful as it is. But yes, technically you can do this with any wine. You can do this with any beer. You can do it with any food product. What it boils down to effectively is cost, right? Whether if churches can afford to make CRISPR edited wine, then, I'm sure the Vatican can, but I don't know about the others. Sure, it's a possibility. See, you have to understand that this is a tool, and this tool can be used to make anything. I mean, right from your medical, it can be used to generate, organs. You can create a new liver today using CRISPR technology. So all the bad effects of alcohol can actually be made good by, using CRISPR on the other hand to generate liver cells, right? So that's a great question. Thank you.
Hello, Vishal.
Yes.
Here. Middle.
Yeah.
Hi. I think this was very exciting as well as scary overall. So I had two questions. The first one is, I think this can solve a lot of problems which is right now happening in Delhi, right? Like farmer protest and all of them. But is this already under production? Because I've read some time back, Singapore is putting a lot of investment in this area. That's one. The second question is, I also read recently that humans, due to this evolution, we have lost a lot of gut bacteria in the last couple of centuries. But this is gonna surely accelerate that further.
Okay, so you use the word scared, right? Scary. Now that comes from an impression you already carry, right? And I think that sometimes that's the problem. We are all fed certain types of information that may or may not be factually and scientifically validated. It may be a spin that somebody is actually putting. Like I said, AI creating job loss for developers type of story, right? So here's something for you guys to chew on, right? Since 1996, 90% of corn and soya bean grown in the United States of America and consequently finding its way into every single processed food on earth has been made from genetically modified organisms. Okay? Has that done anything bad to you? Sure, processed food has done bad things to you, but can you blame that on genetically modified? No, because genetically modified organisms go through a rigorous process of testing, validation. There are people who know much more than you and I and WhatsApp University about the subject that spend days, years in validating the science and the safety aspects of these products before it's released for consumption. Just so you know, Japan, for example, has created a transgenic fish that is in the market today, right? So I don't think Japanese society is going to accept some hobo coming and just putting something on their plates without it going through regulatory approval, right? So I think a lot of this is, you have to understand that there is significant, strong science that goes into safety, and the ethics is also highly debated when these products hit the market. So that's how and about the gut bacteria, I don't know enough about it, so I cannot comment, but I would again imagine that these are one of those scary stories that, like, in 1960s people said that when calculators were invented, all accountants will be out of a job.
Mike, please.
That's okay, I can hear you. I'll rephrase your question.
Are we looking at a wonder supplement which will take care of all our nutrients and required, kind of food for us and the natural food for just for taste in future? Something is a supplement which will give us all we need?
So I wish there was that supplement, but I don't think science has identified that one supplement as yet. Right, those are largely tall marketing claims. If you ask Vishal Menon, he'll say curcumin because Synthite is the world's largest manufacturer of curcumin from turmeric. Right, so it depends on who you ask. So the point is that there is no such super nutrient that will address. There is no panacea. I think the idea is that, but there will be significant amount of more nutritional or nutrition-oriented products in the market at much lower prices. Food will become much more functional. For example, today, if you're eating vegetarian food, you will soon have vegetarian food which comes with natural vitamin B12. Now, you know that most vegetarian food lacks vitamin B12. That's the only problem with a 100% vegetarian diet, right? So, in the future, there could be B12 or vegetarian source that is naturally, coming out of the vegetables you eat. So those sort of problems, by all means, I think this technology has the power to solve. But I don't know if there'll ever be a panacea that will, cure everything.
Yes. Any more questions? I think that was a very, very interesting session. We had a small class on